Welcome to The Explainer. Today we're diving into one of the most fascinating and frankly weirdest families on the entire periodic table. They're all around us, from the air we breathe to the very tips of our matches.
So, let's start with a number you're intimately familiar with whether you know it or not. 78%. That's how much of the air you're breathing right this second is made of one single element, nitrogen. It's kind of the ultimate wallflower at the chemical party, mostly just keeping to itself.
Okay, so let's dig into that, because that simple question, why is it a gas? It opens up this fantastic story about its entire chemical family. A family that gets heavier, stranger, and way more metallic as you go down the list.
All right, let's get formal for just a second. This family has an official address, Group 15 on the periodic table, and their family name? The Pnictogens.
That name, Pnictogen, actually comes from the Greek word pnigien, which means to choke. A pretty ominous nod to nitrogen gas, right? And what makes them a family is that shared outer electron structure you see here. That's the source of all their shared quirks and characteristics.
And here's the lineup. We start with the super familiar nitrogen, then move to the fiery phosphorus, then we get into the notorious metalloids, arsenic and antimony, and we finish up with the heavy metal, bismuth. Quite the cast of characters, huh?
And this slide, it captures the core trend perfectly. As we travel down the group, the personality of these elements completely transforms. We go from true nonmetals at the top, through that murky, kind of in-between ground of metalloids, and we land on a proper metal. It's really a beautiful snapshot of how properties evolve across the periodic table.
So let's zoom in on the most famous member, because nitrogen isn't just the leader of this family, it's the rebellious firstborn. It plays by a completely different set of rules than all of its heavier siblings.
And its rebellious nature really boils down to these three key things. It's tiny, it's highly electronegative, which is just a fancy way of saying it's incredibly greedy and holds onto its electrons super tightly, and it doesn't have these extra d orbitals, which you can think of as extra rooms in the atom that the bigger elements have. This unique combo forces it to play a totally different chemical game.
Now, this is the most glaring difference, and it's where we started. While phosphorus, arsenic, and the others are all solid materials at room temperature, nitrogen just floats around as a gas made of these little two-atom molecules. The air itself is proof of just how unique nitrogen is.
And the reason for this is fascinating. Two nitrogen atoms are locked together by an incredibly powerful triple bond. At 946 kilojoules per mole, it's one of the strongest bonds in all of chemistry. This is what makes that N2 molecule so stable, so unreactive, and so perfectly happy to just float around, minding its own business.
So here's the crucial question. If nitrogen is so stable and unreactive, how do we ever get it to do anything useful? Well, it takes some of the most powerful and important industrial processes ever invented.
This is the big one, the Haber process. To break that triple bond in nitrogen gas, you need immense pressure and high heat, all while using an iron catalyst. It's a total brute force method, but it lets us pull nitrogen right out of thin air and turn it into ammonia. That's the foundation for pretty much all synthetic fertilizers on Earth, and arguably the single reaction most responsible for the massive population boom of the 20th century.
And this is a perfect example of a chemical chain reaction. We take the ammonia from the Haber process and we feed it right into the Ostwald process, converting it into nitric acid. This becomes another cornerstone chemical used for everything from, more fertilizer, to dyes and even explosives.
All right, next up is nitrogen's eccentric younger sibling, phosphorus. If nitrogen is stable and aloof, phosphorus is the complete opposite. It's a reactive chameleon that exists in some dramatically different forms. These different forms are called allotropes. And it's really important to get this. These aren't just different colors of the same stuff. They are chemically the exact same element, but their atoms are arranged so differently that they become entirely different substances with wildly different behaviors. I mean, just look at this comparison. It's wild. White phosphorus is a total nightmare. It's highly poisonous, it bursts into flame on contact with air, and it even has this eerie glow-in-the-dark thing going on. But if you just heat it up without any air, it rearranges its atoms to become red phosphorus, a stable, non-poisonous powder that's so safe we literally put it on the side of a matchbox. Same element, two totally different worlds. So, the elements themselves are fascinating, but their true power really shows up in the compounds they form. This family creates a huge range of important and sometimes dangerous substances. Let's do a quick tour.
Nitrogen alone is a master of disguise. As you can see, it can bond with oxygen in a whole bunch of different ways, creating this whole suite of oxides. This gives us everything from nitrous oxide, or N2O, you know it as laughing gas, all the way to nitrogen dioxide, NO2, that familiar brown gas you see in smog.
The phosphorus compounds are just as varied. You've got phosphine gas, which is notoriously poisonous and smells absolutely awful, like rotten fish. But you also have these vital industrial tools like phosphorus trichloride and pentachloride, which chemists use as powerful agents to add chlorine atoms to other molecules.
So just think about it for a second. This one single column on the periodic table gives us the stable air we need to live, the reactive chemistry that feeds billions of people, and the bizarre glowing materials of science fiction. It's a complete story of chemical diversity, all in one family. It really makes you wonder, what other elements are out there, hiding world-changing secrets in plain sight?